So today we're going to talk about chemical reactions. So our objectives for this lesson is to identify the parts of a chemical reaction, explain why chemical reactions release or absorb energy, summarize the importance of enzymes in living things, and identify and explain how the different factors affect enzyme activity. So a chemical reaction is a process by which atoms or groups of atoms in substances are reorganized into different substances. So in essence, a chemical reaction is when bonds are broken and then reformed into other compounds or other molecules during a chemical reaction. Some examples of chemical reactions that take place could be digestion of food within your body. So as the stomach starts to break down and pepsin is used to break down food in your stomach, that's an example of a chemical reaction. Healing the scrape on your elbow. The actual healing process is a result of a bunch of different chemical reactions. Muscles and bones growing and developing, that's also the result of chemical reactions as well. So a chemical reaction is shown in a chemical equation. So scientists express each component of a reaction in a chemical equation. Now the reactants are elements or compounds that enter the chemical reaction, and they are typically on the left side of the arrow, whereas products are elements and compounds produced by the chemical reaction, and they are found on the right side of the arrow. So here on the left-hand side of the arrow, we have our reactants, and then there on the right-hand side of the arrow, we have our products. So conservation of mass states that matter can be neither created nor destroyed. So all chemical equations must show a balance of mass. So what does this mean? That means the number of atoms of each element on the reactant side must equal the number of atoms of the same element on the product side. And coefficients are used in order to make the number of atoms on each side equal. So if we take a look at this chemical equation down below, this is the chemical equation for, should switch just the green, because this is the chemical equation for photosynthesis. This is something that you will be required to know when we go on further to talk about photosynthesis and respiration. So this is the chemical equation for photosynthesis. Over here we have carbon dioxide, here we have water, and then on the product side, we have sugar and then oxygen. So if we take a look at any one element, so we're going to take a look at oxygen first. We see that carbon dioxide, there's 2 oxygens in carbon dioxide. So we can count 1, 2. But then this suffix means that there's 2 oxygen. However, there's a prefix ahead of carbon dioxide, and that's the prefix 6, or coefficient 6. And we'll take 6, multiply this by 2, so that's 12. So really, in fact, we have 12 oxygen on this side, or 12 oxygen within this carbon dioxide. Now, if we take a look over here, we've got 1 oxygen for every 2 hydrogen atoms. So this 6 times 1 essentially is 6. So 6 plus 12, so we've got 12 oxygen here, we've got 6 oxygen here, so we have a total of 18 oxygen on the reactant side of this equation. Now if we take a look over here, we've got 6 oxygen for sugar, and then 6 times 2 is 12, so we've got 6 oxygen here, we've got 12 oxygen over here, so again we've got 18 oxygen on the product side. So we're looking at conservation of mass here. We started out with 16 oxygen going into the reaction, and even though the reactants bonds were broken and rearranged into sugar and oxygen, we still have 18 oxygen on the product side as well. So the energy of chemical reactions. So the key to starting a chemical reaction is energy. All chemical reactions require some input of energy in order to move from their reactants to their products. Most compounds in living things cannot undergo a chemical reaction without energy. In fact, chemical reactions that take place in our body would occur too slowly to support life if we didn't have both energy input and enzymes to help those chemical reactions go faster. So activation energy is the minimum amount of energy needed for reactions to form products. So activation energy is the energy needed to start a chemical reaction and go from the reactants to the products. Now the peak of the graph here represents the amount of energy that must be added to make a reaction go. So we're looking at this energy diagram. This is the reaction's progress going from left to right, and energy going from bottom to top. We have our reactants here, and then the peak of this here is showing that the amount of energy, or the activation energy, the amount of energy needed to get these reactants to go all the way over to the products. So if we take a look at this energy diagram here, this reaction is exothermic, and what that means is that it releases heat energy as the reactants go, as we go from reactants to products. So if we take a look, reactants are higher in energy than the products, and so when we go from our reactants to our products, we're going to release energy in the form of heat. So this is an exothermic reaction. So the energy of the product is lower than the energy of the reactants, so we're going to get this nice release of energy here. If we take a look at this energy diagram here, this reaction is endothermic, and this is where you're going to get an absorption of heat energy. So the energy of the products is going to be, in fact, higher than the energy of the reactants. Oops. So if we take a look at the reactants in terms of their energy is quite low. The activation energy is going to be very, very high, so we're going to put in a larger input of energy, and our products are going to be higher in energy than our reactants. So this energy diagram is showing an endothermic reaction in which the reactants are in fact lower in energy than the products, and we're going to get an absorption of heat energy. So if you were to, in a test tube, carry out an endothermic reaction, the test tube would in fact feel cold at the cold to the touch, because you get an absorption of heat energy. So an enzyme is what we call a catalyst, and a catalyst is a substance that ends up lowering activation energy, and which is the energy needed to start a chemical reaction. So if we take a look at our energy diagram here, we've got our reactants over here, our products over here, and if we look at our activation energy without an enzyme, it's actually quite high. But if we use an enzyme, our activation energy is decreased, which is going to enable the chemical reaction to go from its reactants to its products a whole lot faster. And we don't need to put in as much energy in order to get that reaction to go forward. So a catalyst does not increase how much product is made, and it does not get used up in the reaction. So we're not making any more product by using an enzyme, and an enzyme is something that can be reused over and over and over and over and over again, as long as we still have products, or still have reactants. So an enzyme is what we call a biological catalyst. It's designed to speed up chemical reactions in the biological processes, and it does this by lowering the amount of energy needed to get reactants to go to their products. So how do enzymes work? So how do enzymes work? So the reactants that bind to an enzyme are called substrates. So if you hear the term substrate, also know that we can replace that word substrate with the word reactant. And enzymes have a specific site called the active site in which the substrates fit into. And the specific and when the substrates fit into the enzyme is going to create a enzyme substrate complex, and it's going to result in products being formed. So here we go, we have two substrates. They're going to fit in quite specifically to this enzyme, and then the enzyme is going to lower activation energy weaken those bonds in those substrates and allow for a reaction to take place a lot quicker, and we're going to get our products as well. So here's another example of enzyme activity. Here we have an enzyme sucrase. We know it's an enzyme because it ends in ASE. So we've got sucrase, we've got our active site, and here we have our substrate sucrose. This is a carbohydrate because it ends in OSE. So the sucrose is going to join or going to fit into the active site. The substrate is going to bind to the enzyme. We've got our enzyme substrate complex. Water is going to be added to it, so this is hydrolysis that is taking place. The enzyme is going to weaken the chemical bonds between the different monosaccharides that make up sucrose, and with the addition of water, we're going to break that apart into its monosaccharide forms, glucose and fructose. And there the enzyme is ready to carry out that chemical reaction again of breaking down sucrose into its monomers, glucose and fructose. So an enzyme is very specific. We often use the analogy of a lock and a key. So there's one substrate to one enzyme. So the substrate is very specific to the enzyme. So the enzyme can either catalyze a reaction going forward, taking a substrate and breaking it up into two products, or taking two substrates and then putting it together to form a product. But if the substrate does not fit the enzyme, the chemical reaction is not going to go forward. So if the key fits into the lock, you'll have a reaction take place. If the key doesn't fit into the lock, you're not going to have a reaction take place. So the naming of enzymes. Enzymes typically end with the suffix ase, and the rest of the name of the enzyme is often derived from the name of the substrate. So lipase breaks down lipids, protease breaks down proteins, maltase breaks down maltose. So if you encounter something that ends in ase, 9 times out of 10, you're going to be dealing with an enzyme. So how can we alter enzyme activity? So we know that enzymes are very specific to their substrates, but they're also very specific to the environment in which they work. So temperature can affect enzyme activity. It can either cause enzyme activity to go up, or it can cause enzyme activity to go down. So enzymes work in very specific environments. So if we take a look at this chart up here, this graph up here, it says the optimal temperature for typical human enzymes, which is around like 35 degrees centigrade, which is about 98.6 degrees. Okay, so most of the enzymes in our body work best at 98.6 degrees. If our temperature was to increase above 98.6 degrees, around 103, 104 degrees, and we couldn't get our temperature to go back down, then our enzymes in our body are going to start to denature or break down and fall apart. If that happens, then those enzymes are not able to carry out any sort of chemical reactions in our body, and we might end up dying as a result of that. There is a specific type of thermophilic bacteria. Thermophilic means heat-loving bacteria. And if we take a look at the enzymes in thermophilic bacteria, we find that those enzymes actually work at a higher temperature, close to about 78, maybe 77 degrees centigrade. So depending on the organism, enzymes work at very specific environments. So obviously heat-loving bacteria, those enzymes are going to be able to work at a higher temperature than, let's say, our enzymes, which work at about 38 degrees centigrade. Also, enzymes work at very specific pHs. So the optimal pH for pepsin, and we know pepsin is an enzyme that is found in the stomach, the optimal pH for pepsin to work at is a pH of 2, which is similar to the pH of hydrochloric acid that is also found in the stomach. Now, if we were to change the pH of the stomach to, let's say, a pH of 8, pepsin would no longer function. And the reason for that is that The active site of the enzyme would change shape, the substrates wouldn't be able to bond to the active site of the enzyme, and we wouldn't be able to catalyze a reaction anymore. Trypsin is a enzyme that is found in the small intestine. It's used to break down some proteins as well, and we can see that the pH of the small intestine is close to around a pH of 8. It's slightly basic. So if trypsin was to be found in the stomach, trypsin wouldn't work because it's too acidic in the stomach for it to function. The active site would change shape, substrates would not be able to bind to the active site, and that enzyme would not be able to catalyze any reactions. We can also alter enzyme activity by either increasing the concentration of the enzyme or increasing the concentration of the substrate. So if we have, let's say, a lot of enzyme and very little substrate, that reaction is going to go very, very fast. Okay, because we've got a lot of enzymes, so we've got a lot of enzyme available to catalyze reactions, and that chemical reaction is going to go forward very, very quickly. If we have a very little bit of enzyme but a whole lot of substrate, that reaction is going to go very, very slowly. So think of it this way. Let's say that you have to paint your house one weekend. If it's just you painting your entire house, that's very little enzyme with a whole lot of substrate. So you being the enzyme because you're the painter and the substrate being the house. It's going to take you forever, the whole weekend, to paint your house. However, if you grab 15 of your friends and you have to paint your house, it's going to go by a whole lot faster for you to paint your house because you've got a bunch of other people helping you. That's the idea behind enzyme and substrates and altering the concentration. So sometimes you can have the presence of a coenzyme. These are what we talked about before. These are your vitamins and your minerals. So vitamins and minerals can act as coenzymes, and some of these substances are needed in order for an enzyme to function. So they sort of act like switches where they turn the enzyme on or off, or they slightly change the shape of the active site, allowing it to bind better to certain substrates, things like that. So now, having watched this, you should be able to identify the parts of a chemical equation, so the reactants and the products. You should be able to explain the importance of enzymes in living organisms, the fact that they're designed to catalyze chemical reactions and speed those chemical reactions up in the body. You should be able to describe how enzymes work, especially in terms of the lock and the key analogy, and describe how different factors such as temperature and pH, as well as concentrations of enzyme and substrate, affect how quickly a chemical reaction would take place. I hope you found this helpful, and I'll see you next time. Bye.